Hi, my name is Bradley Bowers. We're going to cover topics 5 through 12. The first problem deals with topic 5, internal fluid flow with friction loss for laminar and turbulent flow, and topic 6, pump analysis using net positive suction head. So here's the equation for net positive suction head available. It has the known values and the sources I got them from. We're going to find the height of water at which cavitation occurs. We're going to assume that V1 is negligible compared to V2, that the head available equals the head required at cavitation, first turbulent flow, the temperature to get the water properties. We're going to disregard exit frictional effects and the work of the pump based on where we drew our points. Using the extended Bernoulli equation to solve for H, we're first going to solve for the velocity and then get the Reynolds number, which is definitely turbulent. So we're going to use the F prime term for turbulent flow to get script F, which gives us the head available. In part B, we're now going to assume laminar flow. So we're going to use the F prime term for laminar flow and then get a new script F and a new head available, which is negative, which means that cavitation would have already occurred. This is clearly a poor assumption considering the size of the pipe and the flow rate going through it. Next covers topics 3 and 7. I'm only going to talk about topic 7, flow through porous media. Here we have some more known values and the sources that I got them from. We're going to find the superficial velocity. We're going to make some assumptions based on the points that we drew. Laminar versus turbulent is not known for this problem, and the viscosity of blood is constant, so therefore it behaves like a Newtonian fluid. Going to skip the extended Bernoulli equation, but that's how we get the script F term in this equation for flow through porous media. We're going to use our known values to get A, B, and C, which will then solve the quadratic to get the superficial velocity. In part B, we can then plug that into the equation for Reynolds number through porous media and find that it's laminar flow. The next problem deals with topics 2 and 8. I'm only going to talk about topic 8, external fluid flow. Again, we get a temperature and some known values using this source. We're going to find the drag coefficient. And we're going to assume that at the terminal velocity, acceleration is 0. The bubbles models a sphere, which means the area projected is going to be the area of a circle. In this problem, we're going to derive the equation for the drag coefficient, CD, using a force balance, then use our known values to get a number. In part B, if we assume that the density of the fluid is much, much greater than that of the gas, so buoyancy is negligible, we see that the value is very close, so yes, this would be a reasonable assumption in this problem. The next problem talks about topic 9, compressible flow. So we have a refrigerant coming out of a dust-off can. At a specific temperature, we can then look up the values for this refrigerant from these sources. We're going to find the velocity, the stagnation temperature, pressure, and density coming out of the can at a Mach number. We're going to assume isentropic, ideal gas behavior, and constant heat capacities. So here's the equation for the Mach number. Here's the equation for the speed of sound. Here's the equation for K, which will get us C. Then we can plug that in and get V. We can then solve for the stagnation temperature. And if we take the stagnation temperature divided by T, then we can get the stagnation pressure and the density. For the last problem, we're going to talk about topics 10, 11, and 12, macroscopic mass and momentum balances, boundary conditions, and the analytical and numerical solutions to Navier-Stokes. So again, we have some known values. Here's one we had to look up using this source. We're going to find the velocity profile for this problem analytically and numerically, and then gauge what assumptions were made that may not be accurate. We're going to assume laminar flow, fully developed, pressure difference is about linear, steady state, incompressible Newtonian fluid, no gravitational effects, and irrotational flow. Our boundary conditions are no slip at the walls and symmetry at the center of the pipe. We're going to apply these assumptions to the continuity equation and the momentum balance in the z direction, then integrate to find our analytical solution using our boundary conditions along the way, and here is the analytical solution. We can also apply the chain rule to get this equation, and then apply finite differencing to replace the derivatives and get this equation about a node, and I will show the Excel data sheet at the end of the video. The big assumption here that is not good for this problem is that blood acts like a Newtonian fluid, so that viscosity is constant, and in fact it is a non-Newtonian fluid and exhibits shear thinning behavior. And here's a Excel data sheet for the finite differencing. We have some known values. The boundary conditions are in green. In white, we have the radius of the pipe, and blue is the finite differencing solution, which are the blue dots here on the graph, and in orange is the analytical solution for comparison, and that is the line.